Here we discussed the so-called Lorentz group. This group is important because it describes the symmetries of space-time in special relativity. So it is something related to special relativity. Special relativity is a subject very important also in quantum field theory, for example. So these transformations are also really important when we discuss the symmetries of fields and to understand how particles behave in quantum field theory and so on. So let's not delve into these details here because we are going to dig deeper into the mathematics and try to understand it intuitively, quote unquote intuitively. Anyway, the Lorentz group is central to understanding how physical laws remain invariant under changes in the reference frame for observers moving relative to each other. Now, in Minkowski space, we have the metric tensor era mu nu. Let me zoom out a little bit. Era mu nu, which is a diagonal tensor of the kind 1, 1 minus 1 minus 1 minus 1 on the diagonal, and then we have a bunch of zeros outside of the diagonal. Sometimes it might be defined with the opposite sign, so you might have a minus here, a plus here, a plus here, and plus here. But with this kind of signature, it's written like this, so it's signature plus, minus, minus, minus. The signature gives us the signs of the terms on the diagonal. So they can be either 1 or minus 1, plus 1 or minus 1. We have the following set of coordinates, which we labeled with the letter mu. So mu can be either 0, 1, 2, or 3. And the components of x mu are given by x0, which is ct. So this is x0, which is given by the speed of light, and the time measured according to a certain reference frame. So we are in the reference frame, and the coordinates that we use in this frame are given by x0, x1, x2, x3. Now, we know that in special relativity, there is a quantity which is invariant. So, for example, if we consider x mu, and we take this product, x mu, so we have to sum over mu. If we change our reference frame, this quantity here should be invariant. I will tell you a little bit more about it to revise some concepts that one sees in special relativity. This is equal to x mu era mu nu x nu, and of course it can be spelled out like this: x0 squared minus x1 squared minus x2 squared minus x3 squared. Now, if we consider a Lorentz transformation, we are going to label the transformation like this. So x prime is equal to lambda, capital lambda, x. So if you want to see this in components, it would be x prime mu equal to lambda mu nu x nu. So this is the same as this without writing down the indices explicitly. We can substitute this expression in the invariant. So in particular, we can rewrite the invariant as x prime mu, which can be also written as x prime mu, era mu nu, x prime nu. And we can substitute this expression here and here to derive some meaningful quantities. So this is equal to lambda mu rho x rho era mu nu lambda nu sigma x sigma, like this. Now we have to set this quantity here equal to x rho era rho sigma x sigma, because this quantity here should be equal to x mu, or if you want, since these are dummy indices, x rho, this should be equal to this, which can also be written by using the metric tensor like this. So if we impose this relation, we find that we find the property of Lorentz transformations which they should satisfy, and the property is the following: lambda mu rho, era mu nu, lambda nu sigma must be equal to era rho sigma. And without writing down the indices explicitly, one could also write lambda transpose era lambda equal to era. So it can also be written like this in matrix notation. So this is a matrix, this is a matrix, and so on. These are matrices. You can see that we have a transpose here because we are summing over this index. And if you remember, if you have two matrices where this first index is the row index and the second index is the column index, for example, you have two matrices A and B and you take the transpose of A, this is a coincident with the summation over some index j, a j I b j k. So the overall matrix will depend on the two indices I and k. And you can see that we are really summing over this so we are summing over the first index of the first matrix and the first index of the second matrix, because this is transposed. This can also be written as A transpose Ij. This is the usual product when you have to multiply two matrices. Now let's investigate a little bit more this kind of transformation here. In particular, these transformations tell you the ways, they give you the ways in which the invariant quantity indeed remains invariant. So it gives us the symmetries of the Lorentz group, because this quantity here remains invariant under such a transformation. For example, if we change the three components x1, x2, x3 with a certain rotation matrix, so for example, let's define this as x prime 1, x prime 2, and x prime 3, we rotate these three components, so here we have x1, x2, x3, you can easily check that indeed this quantity here remains invariant, because we are preserving the sum of the squares. So x1 squared plus x2 squared plus x3 squared must be equal to x prime 1 squared plus x prime 2 squared plus x prime 3 squared. So it means that Lorentz transformations also contain rotations. They are contained in this object, which is also a matrix, lambda mu rho. But these objects also contain the so-called boosts. What is a boost? It is something that one encounters in special relativity. So for example, if we consider the two coordinates x0 and x1, we can boost them, so we can boost along the x direction, which means that we are using a Lorentz transformation to move from a reference frame to another, which is characterized by the components x0 prime and x1 prime, but this frame is moving with relative velocity v along the x-axis with respect to this frame here. And the transformation is of the following kind. So we have x1 prime equal to x1 minus vx0 divided by c, the speed of light, and this is multiplied by gamma, where gamma is equal to 1 minus v squared over c squared to the power minus 1/2, which is just the Lorentz factor. This is called the Lorentz factor. And we have something similar for x0 prime, which is given by x0 minus vx1 divided by c times gamma. So it is something like this. You can define such a transformation. You can show that with such a transformation, this invariant quantity indeed remains invariant. So this inner product, this is an inner product in the Minkowski space, it remains invariant. Now, when we discuss important transformations in physics, but also in mathematics, we of course have the Lorentz group, the Lorentz transformations. The Lorentz group contains the Lorentz transformations, but we also have the so-called Poincaré group. This group is important because it generalizes the Lorentz transformations. In particular, instead of considering just a transformation of the kind x prime equal to lambda x, which is the Lorentz transformation, we simply add a parameter a, which is actually a vector if you think about it, because this is a vector, but we are using just a vector and matrix notation. So this will be characterized by 4 components, and it is simply a translation. What we are doing here is we are translating x prime. So from lambda x, we go to lambda x plus a. We are translating this object, if you want. So all in all, what we are doing is this. We start from x, then we apply a Lorentz transformation, so it can contain boosts and rotations. So if you think about it, we have 3 possible boosts, 3 independent boosts, because we can move along the x, y, and z direction. These are boosts, but we can also have 3 rotations. And they are independent if we think about the x, y, and z rotations. By combining these rotations and boosts, we obtain a general transformation. So we have 3 boosts and 3 rotations. So we have 6 independent parameters. And then we might also have other 4 independent parameters which describe a translation. So we have another 4, and this is not along x, y, and z. This is along t, x, y, z. It is along, if you want, x0, x1, x2, x3. So we have translations along the time direction, along the x direction, and so on. So these are translations. And if you count them, you have 10 parameters which describe our group. Our group is characterized by these parameters and is known as the Poincaré group. It is important to consider transformations with respect to the Poincaré group or also the Lorentz group. So in general, the Poincaré group contains the Lorentz group, so we can talk about the Poincaré group. In physics, for example, a Lorentz invariant theory, which is something that should sound familiar to those that are fascinated by the physics, a Lorentz invariant theory for a scalar field, for example, phi of x, means that both phi of x and phi of x prime solve the equations of motion. And what is the relation between x and x prime? It is simply given by a Lorentz transformation. So we use a properly defined matrix lambda. We use this transformation, and our theory should remain invariant. So it means that it should preserve the same form in 2 distinct reference frames. Now, you can also replace the term Lorentz with Poincaré. So you might also have a Poincaré invariant theory. If our theory is invariant also with respect to translations. So if we have this translational invariance, we might have a Poincaré invariant theory. Otherwise, if we only have a Lorentz invariant theory, it means that it is invariant with respect to boosts and with respect to rotations. So we have discussed how we can define a transformation for a scalar field indirectly, because it means that if we have a Lorentz invariant theory, we have phi of x prime equal to phi of x. And it means, for example, that x prime is given by lambda x, so we are using a Lorentz transformation. And this can also be written in another way. So, for example, we can write x equal to lambda inverse x prime, and we can substitute it in here, meaning that phi of x prime is equal to phi of lambda inverse x prime. Now we can drop the prime, and we can say, okay, our field transforms like this. So phi of x is equal to phi of lambda inverse x. This is the transformation for a scalar field. Similarly, we can also define transformations for vectors, vector fields, and other generic objects, and I will try to explain it a little better. Let's start with the vector field. For example, a mu of x. This is, for example, the electromagnetic potential, the four potential in the electromagnetic theory, electromagnetism, if you want. It transforms like this. We have a Lorentz transformation of the kind lambda mu nu, a nu, and then here, instead of x, similarly to what we did here, we replace lambda inverse x. So this is the transformation for a vector field. You can see that it is more complicated because we are transforming the spatial components with a proper Lorentz transformation, but we are also transforming the field. And we might have a different field phi a, and a is still an integer that can take the values 0, 1, 2, and 3, so you might say it is the same as this. Indeed, it's true, but we are defining the transformation in a slightly different manner. The transformation of this object will be given by a representation of the Lorentz group that I will define like this, d of lambda, and I will be more specific in the subsequent minutes of this video. I want to give you some better intuition behind this object, but you can think of this still as a matrix. So you can think of this as a matrix, so it has two indices, a and b, and here you have phi b, and similarly you have lambda inverse x. So you can see that the only difference between the vector transformation and this object transformation here is given by this. So the vector transforms directly with respect to this Lorentz transformation, but this other object, which is a generic field, for example, the Spinor field in physics, here you have another matrix which depends on this group, which is the Lorentz group, so it depends on the Lorentz transformation, and it means that we have a representation of the Lorentz group. So I will try to be a little bit more specific. So a representation must have some properties, some important properties. For example, the representation of the product of two Lorentz transformations must be given by the product of the representation, so d lambda 1, d lambda 2, and some other basic properties, but so far this is still abstract. I want to show you some more intuition in the subsequent minutes. But another important property is the following. So we have the representation of the inverse of a certain Lorentz transformation must be equal to the inverse of the representation, and the representation of the identity is equal to the identity. So these are some properties that are just some simple properties, but they are still abstract, because if you have never encountered this kind of transformation, you might have some doubts regarding what this object might be. So first things first. In particular, now let me tell you this. Let me tell you that we want to study the properties of the Lorentz group and also the more general Poincaré group. And in order to study the properties, we want to study the so-called Lie algebra of the group. Now, we'll not get into the technical details of what the Lie algebra is and also what a group is in general, but let me tell you that we want to study, in order to study the properties of the Poincaré group, we consider infinitesimal transformations, infinitesimal Lorentz transformations. So, for example, for a Poincaré group where we have a translation parameter a mu and a Lorentz transformation lambda mu nu, we are really considering an infinitesimal Lorentz transformation. So an infinitesimal Lorentz transformation lambda mu nu is given by delta mu nu. So in general, when we consider an infinitesimal transformation, we have something which is close to the identity. So an infinitesimal Lorentz transformation is almost equal to the identity because it's infinitesimal. So it will be almost the identity plus some perturbation, some small quantity, omega mu nu. So we define it to be omega mu nu. Now if we replace this infinitesimal transformation in the formula lambda mu sigma lambda nu rho era sigma rho equal to era mu nu, what you obtain by dealing with by handling these tensors is that omega mu nu should be equal to minus omega nu mu. So it means that omega mu nu is antisymmetric. And actually it makes sense if you think about it, because an antisymmetric matrix has 6 independent components in four dimensions. 6 independent components. So if you want to sketch it, for an antisymmetric matrix, we have zeros on the diagonal because, for example, omega 0, 0 should be equal to minus omega 0, 0, which means that, of course, omega 0, 0 must be 0. And similarly for omega 1, 1, omega 2, 2, and omega 3, 3. So we have a bunch of zeros on the diagonal, and these terms here are equal to minus these terms, minus this, and so on. So I will not write them. But if you count these terms here, you have 6 of them. So there are 6 independent components for a generic antisymmetric matrix in 4 dimensions. And this number is important. And it is not a chance, it is not something random. Actually, it depends on the fact that we have 3 independent boosts and 3 independent rotations when we consider a Lorentz transformation. So this is not something random, it's important, but this is a property, an important property of infinitesimal Lorentz transformations, as you can see. So omega mu nu must be equal to minus omega nu mu. Now, why do we study infinitesimal transformations? The idea is this. If we consider an infinitesimal transformation, so where you have, for example, the identity plus a small perturbation, and we can call the small perturbation A divided by some parameter capital N, where N goes to infinity. Now, if you apply this transformation N times, remember that N goes to infinity, so you're actually applying the transformation an infinite number of times. So this is not really rigorous, but it means that you are raising this matrix to the power n. And what you're going to get when n grows larger and larger, you're getting closer and closer to the exponential of a matrix. And the matrix is this A here. And this becomes a finite transformation. So if you study the infinitesimal properties of the group, you are basically able to understand also the finite properties of the group. This is the idea. And the exponential of a matrix, let me just remind you what this is about. Basically, you have to think that you're really summing, you're considering the expansion of this exponential. So you're summing over k from 0 to infinity. You have a to the power k divided by k factorial. So this is how you can interpret the exponential of a matrix. You are summing the powers of this matrix, and it is easy to conceive these powers, to understand how to raise a matrix to a certain power, because you can multiply the matrix A by itself several times, k times. So this is a finite number and it is also an integer. So you can raise this matrix to a certain power. And then you can obtain this object, e to the a. This is how you can do it in principle. Now, at this point, we consider a scalar function, which might be phi of x or f of x. Let's call it f of x. And we impose Lorentz invariance. So it means that f of x must be equal to f of x prime, where we transform x to x prime by means of a Lorentz transformation. And if you remember, we can also write the same transformation like this. We have f of x equal to f of lambda inverse x. So you might see it like this, where we have this inverse of lambda, which is still a Lorentz transformation. So in principle, you might also write f of x equal to f of lambda x. It depends on how you view the transformation. There are different ways of viewing this transformation. Here it means that basically we are starting from this value, lambda inverse x, which is actually a vector. So we are starting from this point, it is a point, and then by means of a certain transformation, which is given by lambda times lambda inverse x, which gives us the identity times x, so it gives us x, we have f of x. So we are moving from here to here. It's a way of viewing the transformation. It is something different from here, where we are moving from x to lambda x, but it's basically the same. Okay, it's very similar. It's not the same maybe, but it's something very similar. Now, if we consider an infinitesimal Lorentz transformation, this can be written in the following manner. So here we have something like this. We have x lambda, f of x lambda, where we use the indices. We write the indices, and then we have something like this, minus omega lambda nu x nu. So for an infinitesimal Lorentz transformation, for example, we might go to x lambda to capital lambda lambda mu x mu. So this is the transformation, but if this is infinitesimal, we have something like this, delta lambda mu plus. In general, here we have a plus. If we use the same notation that we used earlier, here. Now let me explain it better. So we have omega lambda mu x mu. And what about the inverse? Here, remember that we have the inverse. If we have the inverse, lambda, capital lambda, lambda mu inverse, you can show that when you multiply the inverse by the matrix lambda, you obtain to first order something like this with a minus. So you have a minus omega lambda mu, and that's it. So the idea is this. If you have lambda, so let's write lambda without the indices, you have the identity plus omega. Omega, remember that, is an antisymmetric matrix. And lambda inverse, let's assume that it is true that it is equal to the identity minus omega. If we multiply lambda by lambda inverse, when you do the multiplication, you have I plus omega minus omega, and then you have terms of the order of omega squared. So you can see that indeed this quantity gets cancelled. You simply have to multiply them together. So it's easy to see. If you have the plus in lambda you have a minus in lambda inverse. That's why here I have considered the minus sign. So this is an explanation for that. If we have a Poincaré invariant theory, instead of this relation, we have something similar of the following kind: f of x lambda minus omega lambda nu x nu. And then here we have an additional term, which is a translational term of the kind minus a lambda. So this is just the translation of what we had earlier. And this expresses Poincaré invariance. And since we are considering an infinitesimal transformation, we have to consider that both omega lambda nu and a lambda are small. So we can expand it in the following manner. So this is approximately equal to f of x lambda minus omega lambda nu x nu. And then we have the derivative with respect to the coordinate lambda here. F calculated at x lambda or x, let's just call it x to avoid any confusion. So let's remove this. And instead of calling it lambda, we can call it mu, like this. And then we have something like this, minus a mu derivative with respect to x mu of f of x, like this. And this can also be written in the following fashion. So at first, let me do some algebra here. Let me rewrite this term in the following manner. This can also be written as 1/2 omega mu nu, and then I have x nu d mu minus x mu d nu. And of course here we have f of x. Now, why did I do this and how can I do this? It's quite simple. If you check, omega mu nu is equal to minus omega nu mu. So here I have simply introduced the same term with a minus sign because we have changed the order of these two indices. And remember that they are dummy indices because we are summing over mu and over nu. But if I change the order, I have to be careful because it's as if we are changing the order here, if you think about it. So we are changing the sign, and therefore it's as if we are introducing this minus itself, which would give us 0. But if we put the minus, we can restore the correct sign due to the anti-symmetry property of this object, and basically it's as if now we have a plus a, which is of course equal to 2a, and to get back a, we have to divide by 2. I hope you follow this logic, but it's just a simple manipulation. So this is equal to this by using the anti-symmetry property of this object. You can check that they are the same. And then one more thing that I want to do is the following. So I can also rewrite this as some identity matrix. Then I can rewrite minus 1/2 omega mu nu x nu d mu minus x mu d nu. And then I have minus a mu d mu, and here I have f of x. So they are acting on f of x. What we have derived here, in particular this part, after the identity matrix, so we are not considering the identity matrix here, this part is simply the change of f of x. The change of f of x is exactly equal to this. And we can also rewrite the change of f of x in the following fashion. So we might define it, so this is actually a definition. The change in f of x can be written as minus I times a mu p mu minus I over 2 omega mu nu j mu nu, and they are applied to f of x. So if we expand this variation, you can see that the variation depends on omega mu nu because we are changing infinitesimally by means of a Lorentz transformation, right? So we must have something proportional to omega mu nu and also something proportional to a mu because we are making an infinitesimal translation. So we are making an infinitesimal Lorentz transformation, so an infinitesimal boost, and or an infinitesimal rotation. And of course, since here we have a mu with the index mu, we must contract the index mu with another object which we call p mu, because there is no mu here. And similarly, you must multiply omega mu nu by j mu nu, summing over mu and over nu, because there is no index there. By setting these two transformations equal to each other, by comparing them, we find that p mu can be written as minus I partial derivative with respect to mu, so this is an operator, and we can define j mu nu as I x mu d nu minus x nu partial derivative with respect to x mu, like this. Now, in quantum mechanics, this object here, multiplied by h bar, but that constant is not really important here, and sometimes in physics h bar is also set equal to 1. So indeed, there is a one-to-one correspondence with the momentum. When we quantize a theory, we promote momentum to an operator, and we set momentum, the momentum vector, equal to minus I, the gradient, times the gradient. And if we quantize angular momentum, we indeed obtain something like this. So this is something like a cross product, and it is the cross product between the position vector and momentum, which is proportional to angular momentum. It's exactly angular momentum after quantization. In quantum field theory, this quantity here, this tensor, is orbital angular momentum because it does not contain any reference to the concept of spin. Spin is an intrinsic angular momentum, and it appears in another manner when we transform not scalar fields but vector fields or spinor fields, for example, because there is another index, for example here, that must be transformed according to the transformation that we saw earlier, a transformation of this kind for vectors or a transformation of this kind for spinors. Now I will not do the computations here directly, but they are quite easy to handle if you know how to handle tensors. You can check that if we compute a commutator, and the commutator, for example, between two operators A and B is simply defined to be AB minus BA, which is of course not the same, so it is not equal to 0 if A and B are operators. It would be 0 only if A and B are scalars or if they commute. If these operators commute, it means that the order is not important and we can write AB equal to BA only if commute. So in general, this is not true. Commutations relations are very important to understand the groups, and so they're not only important for quantum mechanics, they are important in group theory to understand how to deal with groups. Now let me just show you what you can derive starting from here, from these two. One can derive the following, in particular the commutator between j mu nu and p rho is equal to I era nu rho p mu minus era mu rho p nu. And by the way, let me add some more comment on j mu nu. You can see that j mu nu, due to the way it's defined, it is an antisymmetric object because you can see that indeed when mu is equal to nu, it is 0, and j mu nu is equal to minus j nu mu. So it is an antisymmetric quantity, and it makes sense to define it to be antisymmetric because omega mu nu is also antisymmetric. When we multiply two matrices of this kind, where one is antisymmetric, the symmetric part of this object would be annihilated. It would give zero contribution, because when we multiply a symmetric matrix by an antisymmetric matrix, we get 0. It's quite easy to understand, right? Because omega mu nu is equal to minus omega nu mu. And if this quantity is symmetric, it is easy to understand that we get a 0 contribution from that. So since a matrix, a general matrix, can be written by the symmetric part plus the antisymmetric part, of course, this symmetric part gives no contribution since it appears here, and of course we might define simply J mu nu by means of the antisymmetric part of that, right? So you have to understand that we have defined J mu nu in such a way that it is antisymmetric by doing this manipulation here, right? So it makes sense. If you try to understand it, it makes sense what we did. And then we also have some other commutation relations between J mu nu and J rho sigma, given by I era nu rho J mu sigma minus era mu rho J nu sigma plus era mu sigma J nu rho, and then the last term is minus era mu sigma J mu rho, like this. And we have another one between p mu and p nu, which is simply given by 0. So it means that the operators p mu and p nu, they commute. These are really important commutation relations because they describe our group. By means of infinitesimal transformations, we were able to write down these commutation relations where p rho, for example, or p mu, whatever, p mu is the generator of Poincaré transformations, whereas J mu nu is the generator of Lorentz transformations. So if we are only interested, for example, in Lorentz transformations, we are only interested in this commutation relation here, which describe the behavior, if you want, of our Lorentz group. This is the so-called Lie algebra of the Lorentz group. Now, this seems very abstract. Indeed, it is abstract. So you might say, what is the point of considering such an algebra, the Lie algebra? We know that J mu nu is given by this expression, and that's it. So, of course, this expression might satisfy this one, but what is the point of considering this complicated commutation relation? So why this commutator? Well, actually, it is technically difficult to explain this because there are many mathematical concepts hidden behind such commutation relations. But let me try to give you some intuition. In particular, we might also start from such commutation relations, which is the Lie algebra. We know that the Lorentz group satisfies this algebra, but this is more general than it might seem, because it is also possible to choose J nu rho or whatever, J with whatever indices, such that it satisfies this relation, but where J is not written like that. As I told you earlier, this J is related to angular momentum, so it is some kind of symmetry with respect to rotations. So it is a rotational symmetry, not just rotations, but also boosts. But in classical physics, for example, you have that angular momentum is conserved if you have some kind of rotational symmetry. Similarly, momentum is conserved if you have some kind of translational invariance. So you can see the generalization here. But momentum, actually angular momentum, cannot be written like this all the time. In particular, intrinsic angular momentum cannot be written like that. And the reason is this. it is possible to find an operator J such that it satisfies this Lie algebra, but it does not satisfy that relation. But if it satisfies the Lorentz algebra, it is still a description of the Lorentz group. And now let me try to conclude this video by showing you exactly this part, because I think that this is actually very important. Intuitively speaking, it is still mathematical, but I try to convey the intuition behind this concept, which is very important in physics as well. And let me consider a field phi alpha, where alpha is a Lorentz index. So this might be a vector field or a Spinor field. And to be general, we will consider a representation of the Lorentz group, and now I will explain more in detail what a representation is. And we see how this field transforms. This field depends on x, and it will transform like this according to some matrix D of lambda. So it is still a matrix, and it depends on the Lorentz group in some way. I will show you how. D of lambda alpha beta, and then we have phi beta, and here we have a Lorentz transformation, and also let's include a Poincaré transformation. So we have something like this: x lambda minus a lambda minus omega lambda nu x nu, like this. So we have this infinitesimal Lorentz transformation, and this represents basically, so this part represents lambda inverse x. And then you also have the translation related to Poincaré, to a Poincaré invariance. We have already seen how to write such an expression. We have something like this. We have the identity minus I a mu p mu minus I over 2 omega mu nu j mu nu. And then here we have phi beta of x. And how do we represent this object? This object, since lambda is still an infinitesimal transformation, it is something of the kind delta alpha beta, or this is the Kronecker delta alpha beta, so it's almost equal to an identity matrix basically, minus I over 2 omega mu nu, and then here I put S mu nu delta alpha beta, where you see that here I have introduced this operator S mu nu in place of J mu nu. J mu nu, as you can see, as you saw earlier actually, is related to the orbital part of angular momentum, because when you expand this function in Taylor series, you see that of course some derivatives appear, and when you compare the two formulas, you have to set this object equal to the cross product between x and the gradient, basically. I'm referring to this formula here. But here we don't have such a possibility, so we don't have to expand anything. We are not expanding a field, so we don't have the possibility of writing S mu nu in terms of derivatives. So this is the idea. And we are considering representations because we have indeed changed the object that multiplies omega mu nu. So this object should still be antisymmetric, but it is different from J mu nu. So that's what you have to think when you write down representations of Lorentz transformations. You can see that you replace J mu nu with S mu nu, basically. If you have a vector field, since here you have lambda alpha beta, you would have a basis of matrices representing boosts and rotations. But that is not the only possible representation, because spinors, for example, would have a different representation. At this point, if you put these two results together, you can say that this is equal to, now we can multiply basically these parentheses with this parentheses, and we can neglect second order terms, because for example when you multiply this by a mu, you have a mu times omega mu nu, which is a second order term, and similarly when you multiply omega mu nu by omega mu nu, you have a second order term. So what you're going to get is something like this. You have delta alpha beta minus I over 2 omega mu nu. Then you have S mu nu plus J mu nu. This multiplies delta alpha beta, and then you also have minus I A mu P mu delta alpha beta, and this multiplies phi beta of x. And if you want, you can simply change this beta with alpha here, and you can cancel this delta alpha beta here, this delta alpha beta here to simplify the expression, and in place of delta alpha beta here, you can simply put an identity operator here. And this is what you get. You can see that we have a generalization with respect to what we found earlier, where we have replaced J mu nu by this summation. This summation represents the total angular momentum, where we have the orbital part of the angular momentum and the intrinsic part of the angular momentum.